Okay, welcome back, everybody. And it's my pleasure to introduce 𝗕𝗲𝗄𝗆𝗆, and he will speak about deep problems with neural network models of human vision and language. So please, the stage is yours.
All right, thank you. I'm very pleased to be here. I really enjoyed the conference, so I appreciate the invitation from the organizers. So I'm going to be maybe a little bit provocative, we'll see, but I'm going to talk about vision and language and neural networks. So the starting point is the many strong claims that people have been making about these models and how informative they are about the brain and psychology. So here's just one quote, but you could have, endless quotes. The empirical reason why artificial neural networks can be called the current best models of human vision is they offer unprecedented mechanistic explanations of human capacity to make sense of complex natural inputs. So again, many strong claims of this sort. Similar, and more recently, there's similarly strong claims being made about large language models. So here's a kind of a representative quote. The results presented here, based on this new generation of artificial neural networks, suggests that a computationally adequate model of language processing in the brain may be closer than previously thought. And again, you could have endless quotes of this sort that artificial neural networks are really getting us a long way towards understanding the human brain. And my claim is that these claims are greatly exaggerated. And I'm going to kind of highlight, I think, three points in my talk today. One is that most people are adopting, I think, flawed methods when making these claims. They draw mechanistic claims based on correlational studies. And correlations are not causal, and they don't support mechanistic claims by themselves. And then part two, when people do carry out experiments that manipulate independent variables to test hypotheses about how a neural network works and compares those to the equivalent kind of experiments in psychology, you'll often find that these similarities disappear. And these similarities, these predictions that you observe in correlational studies might be driven very often by confounds and stimuli that are not actually informative about mechanistic similarities. And then I think there's more kind of a bit of a cultural problem with the field, which is that people are making very strong claims from, I think, often very weak findings, because the field's very motivated at the moment to be publishing claims where claims of similarity are made. It's very much easier to publish work when you say there's a similarity. It's a lot harder to publish when you try to argue there's a difference. And I think that's contributing to a field that's misrepresenting the evidence as well. So I'm going to kind of go through all these points. So, I mean, the standard approach, this is not anything new on my part, it's just an obvious point in a way. The standard way of using models in science is you assess how well they account for controlled experiments that manipulate variables, independent variables designed to test specific hypotheses. You compare performance across conditions to gain insight into how a mechanism works. It could be a brain, or it could be an artificial neural network, I would have thought. So just a very simple example, in vision, you might say, okay, I have a question. Does human vision, for object recognition, what are the properties of a stimulus that drive object recognition? And you might have two hypotheses. You might say, well, it could be the shape of the object, or it could be the texture and the color of the object. So those would be kind of two alternative hypotheses. So people like 𝗲𝗄𝗏𝗍𝗍 a long time back says, well, I can run an experiment to test that. What I'll do is I'll compare how quickly you can identify line drawings of objects versus photographs of objects, and does it make a difference? And the answer in his study was that effectively no. You can do just as well in identifying an object from a line drawing. So all that color or texture or whatever extra features are not contributing much at all in your ability to identify that object. And so that would be evidence that shape is driving performance. But that required an experiment. You manipulated. You took an image and you removed extra features and asked, does it matter? And one thing I'll point out is Julian Hochberg and people back in the 1960s did a kind of a study that, I don't know, I guess you could do it today, but what they did is they with their own child, they prevented their child from seeing any line drawings of objects until, I can't remember how old, 2 or 3. And then they kind of presented the child with a picture of, I don't know, a cat, and said, a line drawing of a cat, not a picture of a cat, and said, "What is this?" And the child said, "It's a cat." I mean, it was no difficulty at all. So you do not need to see line drawings of images to be able to identify them. There's something about the human visual system trained on naturalistic world has an easy facility to recognize the object based on line drawings. Okay, and similarly, you know, cavemen were drawing pictures of buffalo on walls, having not been trained on images of buffaloes on walls. So that's the standard approach. You'd run experiments to test hypotheses and make conclusions based on that. But in neuro-AI or neuroconnectionism, this is not 100% true. In fact, it's been nice to see talks here where people are not really adopting a more kind of psychological perspective, running experiments. But in the field as a whole, there's a strong tendency not to be doing this. Instead, they come from behavioral and brain benchmarks that do not manipulate independent variables to test specific hypotheses. Instead, the question is, how well do these models predict brain activation or behavioral similarity measures or some kind of behavioral measure on naturalistic images? There's a real focus on it's important to work with naturalistic images, and so we will do experiments with naturalistic images. We do not want artificial stimuli, you know, from old-fashioned psychology. We want naturalistic images, and we'll measure how well you can predict brain activation. So that's kind of a philosophy that really predominates, I think, the field of neuro-AI. And kind of as an example of this practice, one of the more kind of famous tools in neuro-AI is this brain score, where hundreds of models are tested on vision and more models in language, trying to get a higher brain score. So here's kind of the basic logic of it, is you, in the case of high-level vision, what you do is you present a bunch of naturalistic images to a model, and you present the same images to a human, or often in this case, macaque monkeys, and you present these images. Is my mouse? What? Oh, well. Oh, there it is. Well, I don't even need to do this, but so here are the naturalistic images, and I can't see it on my screen. Doesn't matter. And you kind of get the brain activations, or you get, you know, across different layers of the neural network. You get the patterns of activation from there. You get the bold signal in the case of fMRI, or single cell recordings in the case of macaques from different brain areas. And you train a linear decoder model from, you say, well, okay, you know, given this pattern of activation in layer X of my neural network, how well I train the model to kind of do as good a job in predicting brain activation in a given brain area. And then the critical phase is you have a withheld set, a set of images from the same distribution of images, but a novel images the model's not seen before, and you see how well you can predict brain activation. And the better the prediction, the better the brain score. And the claim is the better the model is of biological vision. So here's one of the data sets that are used in brain score. Uses this data set from a judge and colleagues, where they presented a bunch of objects that would be you could present these images in different orientations and different poses and scales, and you'd put them in random backgrounds, because the logic was, we want the human or whatever, or in this case the monkeys, to be not being able to classify images based on the background, but on the object itself, but across different poses and so forth. So they presented thousands of images of an object in different poses on random backgrounds that were not diagnostic of the object category, and they want to see how well you can predict brain activation in different areas of the brain. And then you get brain score. So you have this list of, almost 450 models so far are listed on brain score, and they measure how well they actually have a behavioral part and a neural part, and again, an overall measure of how well they can actually predict, in this case, brain activation on a data set like that. And they have a couple data sets, all very similar to each other, that are kind of measuring the alignment in V4 and IT. And you get a similar leaderboard in the case of visions. You have large language models. You measure the brain you predict brain activations in language areas, and then you see how well you can predict on withheld sentences, and you rank models based on their predictivity. But again, they're just naturalistic. There's no manipulation of an image in any way to decide what properties of the image is driving these good predictions, or what properties of the language are driving good predictions. They're just naturalistic images, and that's the important thing. But although that's kind of the philosophy here, I mean, there's an obvious problem with that, is that correlational studies don't support causal conclusions, and they don't support mechanistic conclusions. So one system might predict another system using underlyingly very different mechanisms. I mean, a digital clock can perfectly predict the time in a cuckoo clock, but the underlying mechanisms are not going to be informative. You're not going to learn anything about the underlying mechanisms of cuckoo clock by studying a digital clock, despite perfect predictions. And people always run experiments because experiments are an attempt to avoid possible confounds in driving things. So normally you run experiments to rule out confounds, to test hypotheses. So correlations by themselves are not very, shouldn't be taken as evidence for similarities. And an example is already described in an earlier talk yesterday. A nice example of running an experiment that clarifies the problems of confounds driving performance is this lovely paper by Robert Garros a while back now, where he put the texture of an elephant on the shape of a cat and asked ANNs to classify these objects, and quite confidently these models would decide that it's an elephant, not a cat. And the reason why is texture and shape are both diagnostic of category in ImageNet, and you could use either one. And in fact, the models often rely on texture, not shape. And the only way you ever could find that, you'd never find that out from BrainScore or from any performance unless you ran an experiment where you manipulate things. So here's a study that shows that, this is not just about classification, but it's also BrainScore. It can be driven by confounds. So here's a study that 𝗕𝗲𝗄𝗆 Malhotra and myself recently carried out, where we had access. BrainScore allows you to have a subset of the data is available for public consumption. So we took the brain responses to 3,200 images that depicted these objects in different poses superimposed on random backgrounds. But when you look through that data set, what you find is that there's 168 image pairs, or actually there's more than pairs, as you'll see, but a bunch of examples of the same object in the same pose, but on different backgrounds. So you have the same image of an elephant, but in different backgrounds, or the same exact car in different backgrounds. And so that, because just by coincidence they had that property in the data set, you can then test a hypothesis. You can ask, well, what is driving BrainScore? Is it the object or is it the backgrounds? Because you can manipulate things. That wasn't what they did. They averaged over everything, but in principle, you could just simply ask a simple hypothesis because you can run a post hoc experiment here. So that's what we did. So we had 3,200 images. We trained a regression model, a linear, just like the typical method in BrainScore, and we kind of took these models and trained the model to on the majority of the images, both the images in random poses, but also these images in these canonical poses. We trained a linear regression model, and then we had 69 images with objects that were withheld, the test set. And we could now manipulate these things and see how did the model do predictions. So in one case, we did the control condition, which is exactly what every BrainScore does. You have the same image that's presented to the neural network in the brain. So it's the same exact image, the same object, same background, and you measure how well can I predict the brain activation from these images. That's the standard approach. But we also, because of the nature of the data set, we could ask, well, how well do you predict this image, this head, on this background to this exact identical head in a different background? So we measured the same predictivity, but we just manipulated the background. The question is, now, brain score is supposedly a measure of core object recognition. It measures, it's thought to refer to how well the higher the score in brain score, the better the model is of how you recognize objects independent of its pose, independent of its background. So given that's the hypothesis of what we're assuming, then it shouldn't matter what the background is. In fact, the whole training set was designed to vary the background to make it so it's not diagnostic of the category of the object. But in fact, the vast majority of the brain score predictivity is based on the background, not the object. So these bars here are the overall height is how well you can predict in the control condition. That is the condition that is usually used in brain score, and you get in this case, a correlation of 0.4, which is quite typical of what you find. But when you change the background, the prediction, is cut by, 3/4 or so. And in fact, in some sense, it could be worse than that. So here, in fact, often there was more than just a pair. So we have this particular car in 4 different backgrounds. So we kind of compared, we had the brain score across all the different pairs and took the average. So these bars here refer to the average score you have when you have the same object in different backgrounds. But you could also pick the worst example, same object in the different backgrounds, and there you get essentially a brain score of 0. So the same identical object producing 0 predictivity, despite the fact it's exactly the same object and exactly the same pose. So here's a case where, if you don't ask the question, if you don't test a hypothesis, you're going to misinterpret the correlations you've got. This doesn't seem to have hardly anything to do with core object recognition. Similar things apply to behavioral benchmarks. So again, the typical behavioral benchmark in brain score is lots of naturalistic images, and then you have some similarity judgments, and you assess, how the brains and artificial neural networks judge similar things and have similar patterns of similarity. That's the standard approach. And again, they're naturalistic images. There's no measure typically in brain score, there's no measure of what's driving the similarities, but you can run experiments again, and it's very simple to do this. So there was the brain score team, which I thought was a great initiative. They ran last year at CCN a competition to see who can make models do the worst. So I think that was a good initiative. And so, of course, that was inspiring to me to enter, so I kind of thought, I'm good at making things break. So, Maren 𝗕tože😊, Gaurav Malhotra, and myself entered the competition, and we just kind of generated images that are, out of distribution images, not things that have been trained, but things like dotted line drawings where you need, basic like Gestalt principles of good continuation and things. But everybody can recognize those as bicycles. We have textures that are defining the shapes of objects. And so we generated these things easy to identify for a human, and if these models are good at predicting, if similarity judgments are kind of, behavioral measures on brain score reflect common mechanisms of human vision, then humans can do these just fine, so should models. So we just would flash these for 200 milliseconds and see how well people could do, and see how well models could recognize these things. And humans, not surprisingly, we got 95% across all these different conditions, but models did terribly. So they catastrophically fail. So they get 0.16, where 10% is champ. So we came in second place, unfortunately. But anyways, the models failed. Now, if you now look at the brain score benchmark now, there's actually this model that does amazingly well. So what is that? 98% accuracy. You go, wow, okay, they've improved. But in fact, they haven't really improved, because this is a CLIP model, which has been trained on virtually everything, including, no doubt, line drawings and so forth. And as I mentioned before, a human being can recognize an object like this, having never seen a line drawing before, let alone dotted drawing. So it's, success by itself isn't going to be, what you need is having been trained in a naturalistic world and, ability to recognize it. And that's not the case, I don't think. And there's lots, if you run experiments, there's some of ours, but other studies out here, there's just lots of ways where if you run experiments from psychology that test particular hypotheses about the nature of the shape representations that drive object recognition, the models, Gestalt principles of organization, various kinds of fundamental properties of human vision as demonstrated in psychology, these models often do terribly. Not always, but often do terribly. And so I think these kind of brain score measures are providing a really misleading estimate of of the mechanistic similarity, and just because correlations don't equal causation. Now, a more general problem is people are often making very strong conclusions from very weak findings very often. So let me give you a couple examples. Now, I'll move to the domain of language here. But there's this paper published in PNAS where the authors write, I think in the abstract, we find that the most powerful transformer models predict nearly 100% of explainable variance in neural responses to sentences. And the results presented here, based on this new generation of artificial neural networks, suggest that a computationally adequate model of language processing in the brain may be closer than previously thought. So that sounds pretty good. But when you look at the paper and go to the abstract, you find that first, the explainable variance is only about 4 to 10% in most cases. So it's 100% of 4%, which is not quite as powerful as one might think. But even more problematic is that non-language areas can be predicted just as well. So this 4%, I mean, and that's again in the abstract, and almost certainly it was a reviewer that said, well, how do other parts of them, and it's to me, and that's not commented, but in fact, that undermines the whole premise of the whole paper. If it's not about language, if non-language areas do just as well. And that's kind of commonly the case when people are reporting these similarities in language cases, they restrict their predictions to the language areas and don't report how other parts of the brains respond. And to the extent that non-language areas do just as well, that seems to me seriously problematic for the claims. So here's a more extreme version to me. They did a study where they were, the previous one was with written text. Here's a model predicting a speech in bold signals and trying to see how well you can predict bold signals with DNNs, large language models. And the conclusion is that self-supervised learning can account for a rich organization of speech processing in the brain and thus delineate a path to identifying the laws of language acquisition which shape the human brain. But here's a key figure in the paper. And so here's a self-supervised performance on the model, and it gets a correlation of about 0.03. Which in terms of the amounts of variance accounted for is effectively 0.001% of variance accounted for. And furthermore, a supervised version gets, so the claim is about self-supervision, but it's 0.0001% better performance than a supervised and not much better than an untrained performance. So this claim is so overblown compared to the evidence that's presented. I mean, that is, what can one conclude about language when you account for 0.001% of variance? I don't think very much. And there's also similar claims in the case of recently in language acquisition. So currently there's a lot of claims that these large language models can learn and certainly syntactic, but also to some degree kind of functional, capacities when trained on a diet of human-like experience. So this paper, 𝗕ecie, I can't pronounce that name, but these authors, the title of the paper here is An Artificial Neural Network Language Models Predict Human Brain Responses to Language Even After Developmentally Realistic Amount of Training. Or Vong and colleagues recently, when it came to learning word reference, have a paper in Science, Grounded Language Acquisition Through the Eyes and Ears of a Single Child. So the claim being that these models can acquire linguistic capacities when trained on a human diet of data. And these are thought to be important observations because they seem to start challenging this idea, because, endless long debate about the role of nativism and importance of innate biases. So 𝗕𝗲𝗄𝗆𝗆 has a particularly, strong example of this kind of statement, but it's quite common. The rise and success of large language models undermines virtually every strong claim for the innateness of language that has been proposed by generative linguists. So these strong claims that, the success of these models is undermining the claim that you need some. Now, of course, every model has its own inductive biases, but you do not, according to these authors, need language-specific inductive biases, as demonstrated by models that don't have language-specific inductive biases succeeding with a developmentally plausible amount of data. That's the argument. And I think that would be that would be, to me, a really good use of a large language model to challenge that claim if you carried out the study in a way that supported those conclusions. But again, these strong claims are made in a way that are not justified based on the way their studies are carried out. So let me give you an example here. How am I doing for time? Got a lot of time. So there's this now annual, sort of like a new benchmark. So we have but it's an annual competition called Baby LM Challenge, where you assess how well models perform in various ways in achieving performance on a language benchmark tasks when restricting the amount of training on the model. And one of the data sets, there's different data sets, but one's called this BLIMP data set that measures various syntactic and morphological capacities, like subject-verb agreement and so forth. Some minimal pairs, and you have to decide whether this is grammatical or not, for instance. So you assess these models, and they have various models on this data set and others, and they have these different categories. One of the conditions is called the strict small condition, where you train a model on 10 million words. And that's thought to be equivalent of roughly the amount of language that a child aged 2 to 5 has been exposed to. So that's, and if you look at, so Llama 2 been trained on the internet, gets 0.84 on this BLIMP data set. But this model that's been trained in this very strict condition gets 0.80. So almost as good. Does very well on this benchmark task, having been trained on so few words. So that kind of finding, again, is kind of leading people like 𝗕𝗲𝗄𝗆𝗆𝗆 to argue these claims that Chomsky and nativism is, in general, is rubbish. But when you look more carefully, the training conditions of these models are so different that really no relevant conclusions can be drawn. So for instance, the model that got 0.8 or whatever it was, that won the competition, I think 2024, it might be a subsequent competition, but the same thing will apply. The winning model, yes, was trained on 10 million words, but for 500 epochs. So it's not one time. A child has one epoch of training. This model was trained 500 times. So it's a child 5 years old or whatever that lived 500 times. And also this 10 million estimate of how many words a child is exposed to in those time, those numbers are misleading because 10 million words is an estimate of the amount of words that a child is exposed to, but all words. I mean, not just child-directed speech, but just speech in the vicinity. So all the words that would be spoken in the vicinity, vast majority of which is not directed at the child. So child-directed speech is a small fraction. Some estimates are, in some cultures, tiny amount of information is directed towards the child, and there's good evidence that child-directed speech is far more informative about child learning a language than just, the parents talking about work after, while the child's in the crib. You shouldn't be counting those words towards language acquisition. Certainly not the level of syntax, maybe phonology. But so this 10 million is a gross estimate of the amount of relevant linguistic experience that a child has. These models are trained on text, not on speech. It's much harder to solve the task with speech, because speech, by text, you've already you've solved some of the problems a child has to solve. Word segmentation, various invariances, all these things a child has to cope with. These models have avoided that. It's orders of magnitude more training required when you have a model on speech. So it's more training on more unrealistic data. And how do these models succeed? They have a vast short-term memory capacity. So 𝗲𝗲𝗄 or something has a short-term memory capacity of 1 million words. So you have 1 million tokens in your short-term memory to predict the next token. Now in this model, the model that won the competition only had a short-term memory of 512 words. But a child has a short-term memory of under 4. If you give the model idealized data, much more data, and superhuman memory capacities, and show that the model can succeed, the conclusion is not plausible to say, well, therefore humans don't need inductive biases to learn. It's just not a sensible conclusion. But again, that's just over and over the claim that's being made in the literature. It's also the case that people ignore the problematic findings out there. So for instance, a classic form of evidence for the importance of innateness of language comes from, for instance, observations that children will kind of improve on a language based on degraded input. So a classic study with Nicaraguan Sign Language. There's this case where children in Nicaragua there's kind of historical case where they put children together in a deaf school. There wasn't such a thing as Nicaraguan Sign Language, and the parents put back in the late 1970s, a bunch of deaf children all went to school together, and the teachers were going to teach the children lip reading in Spanish. So they didn't know about sign language, or they didn't care about sign language. We'll teach them lip reading. So the deaf kids, hung out together in the schoolyards, got bused together. And the kids started gesturing together, and they invented a language called, year after year, it became more and more sophisticated. Now it's called Nicaraguan Sign Language. It's a fully formed, grammatically complex language that was invented. There was nobody training these children to learn a language. There's no way a large language model is ever going to learn from, if you just gave it degraded input, it will output degraded output. If you don't have an inductive bias, you're not going to improve on what experience that you've had. But as far as I can see, I've never heard anybody arguing for the innateness of language talking about this data. It seems like that's a really important constraint. One other thing I'll mention is an example of impossible language. So the Chomskyan solution to learning a language from limited data, what you call the poverty of the stimulus constraint. So you have this, that's the challenge of the language acquisition of a child, is to learn from limited data. And Chomsky's solution, you don't have to agree with the particulars of what his innate inductive biases were, but he had something in general called a universal grammar that had two properties. One, it constrains the kind of languages you learn. All languages conform to this universal grammar. And the advantage of that is that it's easier to learn because there are inductive biases that make it easier. There's a cost, which is you can't learn anything. So there's a benefit and a cost. The benefit is that you learn from a limited amount of data. There's a cost, which is you can't learn anything. So that leads to obvious predictions in human language acquisition, which is it should be hard for humans to learn languages that do not conform to universal grammar. And so studies have shown that that happens to be the case. If you give things that are not human-like, they take longer to learn, and you can learn them to some, but it's more like a problem-solving exercise. And if you look at the brain activations, they're not activating normal brain areas of the brain. It's kind of it's like maybe like learning computer code or you know, some kind of other mathematical equations or something like that. So you can solve it, but you can solve it in a non-human-like way. So so if you give humans impossible languages, that's the kind of pattern of results you obtain. It's harder to learn, and in fact, it doesn't activate the right relevant areas of the brain. But artificial neural networks with these kind of that don't have human linguistic inductive biases seem to learn impossible languages just fine. So Jeffrey Mitchell and myself, a while back now, took this large language model that accounts for various linguistic phenomena, in particular agreement between nouns and verbs. And we trained this model on the original corpus from this study, but also generated a variety of impossible languages and asked to what extent the large language model can learn these impossible languages. So one example would be, we kind of put some random point in a sentence and reverse the order of the words after that segment. So something like, the man whose dog barks likes apples would be converted to the man whose dog, special marker, apples likes barks. So you kind of just reverse half of the sentence, make it impossible. The grammatical rules before and after of the marker have switched midway. We had different ones. We had one where we got rid of this hierarchical structure. We had like a repeated word. So a word would, a sentence would go along, and then we just throw in like 24 repetitions of some word, and then on the 25th word you continue forward and so forth. So you'd have this kind of we had this shuffled, I can't remember exactly how we did the shuffled one, but anyways, we had various impossible languages and assessed how did these models learn. And the answer was they learned basically equally well regardless of the language, possible or impossible. There was no particular cost. We did some internal analysis showing that they learned them in the same way, unlike these brain activations. Not only did they learn them just as well, but they learned them in the same way, unlike it seems to be the case of humans. So I was really pleased that Noam Chomsky wrote an article in the New York Times talking about the false promise of ChatGPT, and they cited our work on that. That was great. And I have a paper now that's almost in press, I think, kind of reviewing all this work about to what extent these large language models are challenging the role of innate priors in language acquisition. And it also would apply, I think, these critiques apply to, in the case of this Brendan Lake paper, where they're claiming you don't need inductive biases to learn word reference, but the same thing, words are repeated 400 times, or they provide extra information to the model that isn't available to the child. There's lots of properties that kind of, to me, undermine the claims that people are going to make. So, I think I might be going too fast, but anyways, so my conclusions are, so there are good behavioral and brain predictions, both in the case of vision and language, but these good correlational study predictions are correlational, and you need to know the basis of these predictions. And just doing a correlational study is not sufficient to know whether the basis of those predictions are similar to the way humans perform. And when you do kind of rule out confounds and test hypotheses by running experiments, typically with artificial stimuli, you find out that those predictions are being driven by non-human, they're often confounds, and they're not the basis of how humans are doing it. And researchers are looking for similarities and drawing strong conclusions from very weak outcomes. I mean, I think the field really needs to embrace much more the value of falsification. It's very hard. I have another talk somewhere where I just kind of go through my own experience where endlessly I'm getting in reviews, the comments of reviewers will be, it's not enough to falsify a model, you need to provide a solution. And by solution, they mean make the model like the brain. We're not interested in publishing things that aren't solving the problem. And so, there's just, it leads to a field in where we have over and over again claims, very strong claims, correlations that seem to suggest similarities, and a field kind of with not enough studies showing that these claims are often not supported. So it's possible, but I think that the battle is it's harder to publish critiques than it is, just like null tests are. So anyway, I think that's it. So the way forward, I think we need to focus a lot more on controlled experiments that test hypotheses about how human vision and in language and memory works, and compare those to the same equivalent experiments carried out on neural networks. Promote stronger tests. Don't look for superficial similarities, but severe tests. And I think you have to change the attitudes of reviewers in this field. We have to kind of recognize that falsification is a valuable contribution to the field. So with that, this is my team. A lot of this work was all done I had a great team of people working on an 𝗕RC grant that's finished now, but a lot of these ideas were all based on work that we did together. So thank you very much.
Hi, Jeff. That was fun. I have thoughts. But I wanted to talk about one of the first points you made was about this thing about correlation, and studies aren't doing correlation. And, they're using correlation, they're not doing experiments. Okay. And I think about it quite differently, and I wonder if this would make sense to you if you've thought about it in this way. Like when we started doing 𝗲𝗄𝗎, we had faces and objects that were faces and houses, 2 conditions. And you had to that was all you could get. But then it would be nice if we could have even more conditions, because what if this region is responding to faces more than houses for other reasons? So we added more conditions in. And we got better and better refinement the more we could have condition-rich designs. The more conditions we could have, the easier we could figure out what underlying properties are driving higher responses and lower responses, and try and put labels on those. And so where that has gone into the extreme is we unlocked image-level reliable data. And the neuroscientists have it for fMRI, we're just recently getting there. Now, we don't even have to presuppose things go together the way we think they go together. This face might be represented differently than that face. And if you have reliable data at the image level, you could find that answer. Whereas if you grouped things, you couldn't find that answer. It's like a fundamental difference between blocked. Okay, so the naturalistic experiments run on, 10,000, or take the data set you had with different objects on different backgrounds. Each image is a condition. The experiment is, the experiment is, what are the features that predict the level of a response to each image? It's like 1,000 conditions. And it's not just correlation, it's prediction. I'm going to make hypothesis about how much each image, I'm going to use this data, I'm going to make a fit, how much each image drives it more or less. And that would be correlation. If I just reported it, great, look, I did a linear fit, I can predict this 0.9, done. That would be where it would be a mistake. But instead, the key thing is you take held out images and you have to make a prediction. You have to put your money where your mouth is. If you got the features right, it should work on these other images. And that's the score you report. Now, there's a lot of discussion about how far out of distribution should those be. And the best model, everyone agrees, would be one that not only can do sort of a sample from within the distribution, but also beyond it. Can it do line drawings? Does it generalize? But the framework is still the same, which is look, this is not just correlation. This is a fit and a prediction. And the same way, if you want to causally go, oh, I'm going to amplify based on this tuning curve, I'm going to go, this is a commitment, I'm going to ramp up the features that I think drive it. I'm going to test, I'm going to measure the response, and I'm going to see, sure enough, those actually control the response. Those to me are causal, not just correlational, in a condition-rich experiment. So back at you, does that framing of it in experimental logic make sense and make you feel less worried about some of the scores?
No, but for one thing, correlations do support prediction. So I don't understand this distinction between prediction and correlation. A correlation will allow you to make a prediction, but you may be supporting that prediction based on a confound. You don't know. The point, I'm interested in knowing what are the features that are driving the prediction, not simply prediction. So give a concrete example, you can respond, but let's take an example. It's not out of distribution, really. It's I took a subset of the images in BrainScore and found out, and you could only do this by manipulating an experimental hypothesis, a particular interpretable one, which is it the background or the object that drives a prediction in brain score? And these are the brain score values, these are withheld examples, and I don't see how you could know the answer to that question in the method you're adopting. You would have to do a very particular hypothesis-driven question, which is it the background or is it the object? And in short of that, an item level kind of I just predict out of, test items out of training set and, on an item by item basis, figure out what the overall correlation score. I mean, you need two numbers. You need two numbers in two different conditions. And you compare, not, yeah, but if you
100 numbers in 100 different conditions. It's the extension of that.
Yeah, but just to, I just think you need, rather than overall correlation, I want an effect size of, comparing two numbers rather than a single number. That single number is it's not testing a hypothesis other than, okay, your model, because you could get 100% prediction, and in fact, a lot of these language models, the claim is you do get 100% explainable variance, 100%. But, I don't know if it means anything.
I mean, let's take the case of a single neuron. The format of the answer of what is the feature tuning, that's what you're asking. I want an experiment. I want to be able to understand, is this the foreground or the background? That requires you come at the answer with these are the interpretable handles, and the answer is going to be cached out in these constructs, foreground, background. What they're trying to do is go, I think foreground and background might matter. That's why they put those in there. They put that variation in there. But I don't want to assume that the answer for what's the best tuning is going to fall along those axes. Instead, what they're doing is they're caching out their features in this combination of units in this layer of a network. And that's an image computable feature axis. And now, okay, I don't fully agree with I'm not full in line with the BrainScore platform, so I'm a little bit arguing Jim DiCarlo's line, which I only partially agree with, but I think the experimental logic part is sound. And this is Jim goes, look, I don't even think the answer we're looking for is possible to find if you only look at object versus background. He's so, in terms of how he thinks the visual system untangles object category and invariance, he doesn't think that you'll be able to find answers of the form you're looking for. So it's not, he's going look, as a population, any one unit, you may not be able to, but as a population, can we predict the responses and can we read out certain competencies? So that's coming from a conceptual framework about what kinds of answers should be possible. And that's why each image is its own condition, makes the lowest commitments for what things are the same, what things are different. But then, he later, to his credit, goes, well, some of these are fit better than worse. Which ones were easy, which ones were hard, and why? So that is thinking about all 100 images as conditions and then going, these ones were hard, and then they do follow-up experiments on those because those were hard for the model. Why? They're conditions. Each image is a condition. And a lot of the work going forward works on that level. That's why I focused on this one to talk through, because I do think those are experiments, but they're caching out the scope of answers you could get at a slightly less targeted, the kind of answers you're going to get are these broader ones, right? They're less hypothesis-driven. They're hypothesis-driven in that you had to pick a span of objects to put in the first place. So you're not free from experiment or bias. You have to representatively sample some domain of interest. They could have been not doing visual objects, wouldn't drive that cortex at all. But beyond that, it's a much looser specification of the hypothesis. So now does that change your thinking at all?
I guess I struggle to.
I'll stop.
I mean, everything's an experiment if you just say, I'm interested in correlations and then testing out of sample stimuli. And I don't think that's an experiment testing a particular hypothesis. I mean, just the other example that people could have done brain score endlessly and keep on trying to get higher and higher scores and not know that it was the texture, not the shape, that was driving performance until Robert Garros ran an experiment where he systematically manipulated images in a hypothesis-based way. And you could have done the single, your approach of just, correlating at an item level, and you would never known the answer to that question. And so I just don't understand. I mean, I think we could all agree that what Robert Garros found is important. And in fact, it's motivated a lot of people in the neuroconnectionist camp to try to train models differently or modify the architectures in order for the models to show a shape bias. So they are concerned with that finding, but they never would have found out about that finding had they not ran the relevant experiment. And I think that's over and over going to be the case, that you're going to discover profound failures. I mean, I think it's I would have thought the most basic thing we know about human vision, object recognition, not everything about vision, but human object recognition is largely about a theory of shape. And not only any shape, not just shape is more important than texture, but how parts of objects are organized, the relationships between parts. There's lots about the global properties of shape. There's lots we know about shape from psychology, and lots of research has been done. And until 2019, there was brain score and people were getting excited, and then someone found out it doesn't even pass the first hurdle. It doesn't actually care about shape. And that's really problematic. Now
Or the ventral stream cares more about texture than we thought.
But
someone thought. Or texture is really important in the ventral stream, and how you go from ventral stream representation to labeling in behavior, we got to work on that. Maybe you read out part of it. In fact, when you scan the ventral stream, it responds a lot to texture.
Yeah, well, sure, there's texture, but this is a theory of object. I mean, the models, wherever it occurs, it's a ventral stream or prefrontal cortex. The claim is that how does an artificial neural network do it? Wherever it's done, it does it on texture, and humans do not do it on texture. Now, whether they do it on shape in ventral, in IT, or they do it in prefrontal cortex is an important, interesting question. And the correlations you observe may reflect, okay, seems unlikely to me, but okay, maybe a model trained on object recognition just coincidentally has a very good theory of shape, texture perception in ventral stream. That may be right, but it's not the case that it's a good model of object recognition and core object recognition. That's what I say.
So I have a comment about this discussion, and I think that an underlying issue over this debate is a fundamental distinction between unstructured observations and experiments. And observations, unstructured observations, they're a fundamental part of science. That's how you generate hypotheses. You see what's going on, you come up with an idea, what could be behind this observation. But an experiment, what makes a good experiment is not just having more conditions, it's having a specific hypothesis that you want to test, and then you design your conditions to test that specific hypothesis. Adding conditions without having a hypothesis that you're interested in testing with those conditions, I don't think it's very meaningful. What you're basically doing is increasing the number of unstructured observations. And so in a case of a data set like this, where you have thousands of images, and you want to see if your model can predict the images based on training a subset of them, you're training the model to predict observations, but the model is not really helping you test any particular hypothesis about how it's doing it. And I think that's the fundamental issue that, of course, you can do it with neural networks. You can do it with large-scale data prediction like this. It's just, I think, the examples that Jeff mentioned in his talk are not examples where people are doing this. They're making strong claims about knowing what's going on in the brain, understanding the underlying mechanistic basis of what's going on, when, in fact, they're not. They're simply predicting data. They're training the model on data to predict more data without even having a hypothesis to test. I think that's the fundamental issue there.
I actually wanted to ask a question, but I have to make a comment on this because, first of all, I mean, I think that is another confusion I think that's being added now on top, and we have to make sure we don't get entangled in this. But I think, first of all, I mean, we can make very, very strong conclusions on observational data, which is like the fundamental in a lot of different fields in research, like in ecology, in medicine, because a lot of things cannot be done in randomized controlled studies, and you can still learn a lot. No, you can make causal claims even. Like that's something that's actually one of the key insights that was gained in the last like 10 years is from like causal modeling, that if you have sufficient control, if you have sufficiently large models, that you can make causal claims. They might not be as strong as the claims that you would be making from like running experiments, but you can actually start to make causal claims that way. And it just comes from the constraints that are added by having like a sufficient number of variables. But I mean, the other issue I think that we talk about is I think we should not conflate hypothesis testing and running experiments. I think you can test hypotheses on data that you acquired, and that is not specifically designed for testing a specific hypothesis. So that's where we're getting to the condition-rich designs, which are, by the way, called condition-rich experimental designs, because they're meant to include many different experiments. I'm mixing up myself now. Many different experiments that you can potentially run. So, for example, I can now go and take my many different conditions that I've included into my experiment, and I can now say I want to specifically isolate and focus on the test of faces versus scenes, and then lo and behold, you find phase-selective areas, right? And you can specifically then focus on like specific subsets. The idea is instead of sampling selectively, you actually sample everything. You sample the entire world, and then that way, once you've sampled everything, then you don't have to run like a controlled like experiment anymore. But and the difference. Exactly. Yeah. Yeah, exactly. But I think nobody. Yeah. But that is. I think that's the challenge. Is like I think you don't have to. Don't have to specifically design an experiment in order to be able to run like an experiment. So we don't have to go back and see like, oh no, now I have to run like all of these like individual small scale studies, and oh my God, and you have to like think about like every individual like manipulation. And no, you can actually take the data that we have and you can still do this. You can still run these kinds of, exactly. Yeah, exactly. I think, yeah, no, but I'm not arguing with that, but I just wanted to say that we don't have to, run experiments specifically. In order to test hypotheses, yeah. No, yeah, but you don't have to do that. That's what I mean. That's not the only way to addressing like potential confounds. You can actually control for confounds. But when you use the data itself to control the confounds, you can do both. You can. Sorry, this is two things. You can take a subset of the data and run an experiment in that. You can also just take all of the data. And once you have the variables that you're actually trying to explain, you can see if these variables are then like relating to like the things that you are caring about, and you can control for all of the other factors at the same time. So you can use all of the data, and you can. But exactly, yeah. But that's fine. But that's not the kind of experiment that Jeff is talking about.
Let's also ask.
Anyway. But sorry. So now I want to.
Let's continue the discussion.
Sorry about this. Yeah.
After that.
Well, just to respond so far, and then we can continue. But I mean, you're not sampling the whole world with your net. I mean, so for instance, from your data set, how are you going to reorganize your images to tell me whether it's texture versus shape? You don't have in your data set, you have not manipulated something in an artificial way that you need to do to answer that question. How do you know it's the background versus the target unless, no, in that case, only by fortuitous circumstance do they have the same object in different backgrounds. So if you did that, then luckily you can do an experiment, and that's what I did. But there'll be many, virtually all of the research in 100 years of psychology, none of that data is in your data set because they're all designed simple things that are actually very informative. Are there Gestalt principles? Is it this? Is it that? Is it this? You don't know, and you will never be able to use your data set. You can do interesting things, so I'm not suggesting your data is not valuable, but I'm saying your data set is not, you're right, if you sampled everything, including all the possible experimental, stimuli, then you could post hoc sit around and do it. But you'll never be able to do that because there's an infinity of possible stimuli. So you have to pick stimuli that are very often outside the distribution of your data set because they're not natural. They're line drawings, they're dotted line drawings, they're textured stimuli. There are dots of, that kind of support certain kinds of Gestalt principles. Right. All these kinds of artificial stimuli are not going to be in your data set, and you'll never sample them unless you have a hypothesis in mind, and then you'll construct stimuli for that very particular purpose.
So yeah.
Short answer only, and then to Audrey.
Okay, so okay, so okay, it's fine. It's fine. Oh man, I really want to know it.
So thanks very much for your talks, really elegant. I guess to your list of things that we need to do to improve, I hope it wasn't on there, but it seems to me like we've been, to some extent, we need to be really clear about exactly what we're trying to achieve with this parallel between the networks, between our models and the brain. And I think that what you're doing is you're saying, which is, we've kind of been sold this story, which is incredibly seductive, right? And, people like Nico write so beautifully, that we've been sold this story that the deep neural network is a model of the brain. And you don't have to think about very long about that to realize it's complete, that's never going to be very accurate because it's a 7-layer AlexNet against an enormously complex thing. And so it's never going to, it's not going to be a model of the brain. So that's one type of analogy you might make, is you might say the deep neural network is a perfect model of the brain, but you might also use deep neural networks for some other purpose. You might say, well, let's try and learn about image statistics, or let's try and learn about what's happening in one particular region by setting up a model of what that region does, and you're not trying to model the whole brain. And so I guess, or you might be, one of these people that tries to map, there are people doing maps of fly olfactory bulbs or something, where they're trying to map particular neurons in their network onto particular neurons in the fly, which again is a completely different thing. So there's lots of different things we can do with these tools and lots of different levels at which we can make this parallel. And so I think that we need to get better at articulating, even to ourselves, be really clear about what we're trying to achieve. And sorry, if I can just say one more thing, this rambling thing I mean, we already know, for example, that lots of different neural networks are equally good. We're trained on different data with different architectures, different ways. They all provide equally good models of the visual system, for example, and they can't all be right. So, at some point, we just need to be really clear with ourselves, what are we trying to achieve and how we're going to do that, and yeah.
I agree. Yeah, that I agree. You can definitely use them as tools, and that could be very valuable. You can make some kind of, I would have been impressed about these large language, so take the large language model kind of issue and nativism kind of claims. It would have been super impressive if they had made the models learn with a really realistic data set of stimuli presented to humans. That would be in existence. It wouldn't demonstrate, but it would undermine poverty of the environment, poverty of the stimulus conditions. Now, at the moment, if anything, it lends support to Chomsky's hypothesis that it's not sufficient. And so that, yeah, so it wouldn't be exact, but I do think that would be an example of if you could make a model do something that, someone claims you need to do this, and then a model can do it without this, that's an existence proof that's very valuable. And yeah, and you could, generate, Gibsonian kind of thing, what kind of information is in the world? Well, maybe you could use a neural network to kind of highlight that actually there is structure in the world that's not apparent, but it's there, and that could be exploited. And so you don't have to add this extra information because it's there in the input. So that would be another. So I'm not anti-neural networks, and I'm not even anti. You know, I'm skeptical that these models are good models of the brain, but I'm also not. And I think they're going to be fundamentally different in some respects. But there might be some interesting things that do come out in the models as they are. But you're going to have to test them in a different way to find out. And I think that the bottom line is that they're going to be, 95% not very informative, but there might be a few bits and pieces there that are really informative. But yeah, how you use them is a critical thing.
It's a way of thinking as well, right?
They
provided lots of ways for us to start to think about problems, and that's incredibly valuable. Just this conceptual thing, and probably the other way too, that we've helped the neural network people, the engineers, help them to think about their network. That's why they use psychology words like attention and whatever, even though they claim that sometimes they're not at all inspired by us.
Sorry, I didn't see you.
Hi, thank you very much. Very thought-provoking and corrosive.
Thank you.
So I wanted to ask you two questions. The first one, so Gheiros and Wijkman, like recently, they were arguing that the neural networks are good statistical models for human visual behavior, but not good mechanistic models. And so I wanted to ask you, so is that what you mean when you use the word causal? And then secondly, if you think that they are good statistical models, I think you have argued they are not. What could you propose as an alternative? Because so I feel like even though it's very, very useful to build a model, you need another model to some extent, even though it's super useful to see where the model breaks. Thank you very much.
Mm-hmm. I guess I don't quite know what it means to be a good statistical model. I mean, if it means you can predict naturalistic data well, I suppose it's true, but it won't be a good statistical model if you deal with artificial stimuli. So, the predictions will fail if you go out of distribution from the training set. So I don't quite know what it means to be a good statistical model, but I think it probably is not a good statistical model if you test it more severely. And I definitely don't think it's a good mechanistic model in some respects anyways. I mean, at some level, the visual system is hierarchical, and I expect there are, convolutional systems that, like V1 is, the hypercolumn structure has some kind of convolutional structure to it, which is innate, not learned, by the way. So, what was the other question? The alternative. Yeah, well, I'm happy to try to do more severe testing and, experimental work on neural networks, but I do think this fixation of only relying on image computable models. There's lots of interesting psychological models and, very informative, box and arrow things, dorsal versus ventral streams, Geon models, whatever. I mean, you don't actually, the ultimate model, to my mind, the goal of a model is not to predict. The goal of a model is to understand. And the question is whether these models provide understanding or not. And I think there are a lot of psychological models that provide more understanding than any neural network at the moment. And so this kind of, what is the best model? It's like, okay, it's best at predicting naturalistic image data sets, but I just don't think that is the point of a model. So yeah, I think more work with artificial neural networks, evaluating more severely. I imagine my expectation is we're going to have to change in some profound ways the ways these models work to make them better, but also don't dismiss basic modeling in psychology that I think is very potentially informative.
So I really appreciate the kind of turn that you imposed on the logic from the models. And in some ways, you could look at it and say that the upper limit, the limitations of these models to explain behavior demonstrates why they're not an adequate theory of how the system works, and almost constitute existence proofs for why we need the inductive biases to begin with, because presumably without them, you don't get to the full system. So, and I was wondering, I was thinking, well, maybe the analogy to the Nicaraguan Sign Language for the visual system are the studies that have used congenitally blind subjects to show that you still get the same kind of macroscopic organization. So I wanted to hear your thoughts about, could you invert the research program of these artificial neural networks to actually isolate and identify the inductive constraints that the models don't have, to ask, okay, if you selectively start to include inductive constraints, like for instance connectivity or behaviorally relevant dimensions, does that demonstrate actually the shortcoming of the model in a way that does tell you something about how the brain works?
Yeah, no, I think that sounds like a really good research agenda. So I think, I mentioned briefly, like, there are these studies that show, even before, you get the hypercolumn structure if you do like these kind of Hubel and Wiesel studies on the organization of simple cells and hypercolumns. That occurs in animals in utero, and that occurs in animals, that I've not seen it in anything. So the people point out, and there are these interesting studies, that if you raise a cat in a world in which there are vertical lines only, then they lose these horizontal cells. So it is the case that V1 structure can be modified by experience, but it's modifying a hypercolumn structure that's there from birth. So, and there's, Pinhua Sin or somebody from MIT has done stuff with children that have cataracts, and they take off and they actually acquire knowledge very quickly and things like this. So again, that's kind of an interesting case. And so I think there's a lot more structure than, so these attempts to say, okay, if I train a model on ImageNet, I can get some Gabor filters that look a little bit like V1 structure, and if I do, and then I add more inductive biases by adding lateral interconnectivity, and I can actually get an organization of cells that follow roughly a hypercolumn structure. That's sort of a misguided approach, because it's not there in response to ImageNet. It's there in response to evolutionary experiences. Of a natural world, the brain evolved, but it's not evolved. It's not learned in the same way other things are learned. And but I agree.
Okay, I'm afraid we need to stop here. So thank you again, Jeff.